Today's video, I wanted to talk about power. Part of the reason that I chose power is because I thought that we might not have as much time to devote to it in class, but I wanted to make sure that you were familiar with it. So we've already learned about work, and work is when you apply a force to something and it moves through some sort of displacement. And as long as there's a component of that force that is parallel to the displacement, then work is going to be done. Now, the one thing that we haven't really taken into account when we calculate work is time. For instance, if it took me 100 joules of work to move a box across a floor, it seems to me that it matters how quickly I do it. Because if I have to move that box 20 feet, and I take my time doing it, and I do 100 joules of work, I might feel like no big deal. But if I then try to do it very quickly, it seems like in some way I should be able to quantify the fact that completing that work in a shorter amount of time is going to be different than completing that amount of work in a longer amount of time. And that's where power comes into play. Because power is defined as the rate at which work is done. And so in a very basic definition, well, it's the amount of work done in a certain amount of time. Just work over time. I don't know if I should have done delta. I don't really like the delta. I'm going to get rid of the delta because it's just work. We don't really talk about a change in work. It's just work. So that's basically what we might call the average power, because we're just thinking about the amount of work done in this time interval. So as an example, if I did 100 joules of work in lifting a box, if I did 100 joules of work, let's think about the fact that if I do it in 5 seconds, or if I do it in 1 second. Well, when I calculate the power for those two different time intervals, well, we'll call this one number 1 and this one number 2. The power for number 1 is just 100 joules over 5 seconds, which is 20. And now the question comes up, what are the units of power? Well, we know that we measure work in joules and time is measured in seconds. We actually have a name for 1 joule per second, and it's called a watt. Now you might say, hey, that sounds kind of familiar, and that's because when we talk about electrical energy, we see that unit of watts, or if we think about maybe a light bulb, we see that unit of watts, and so now we have a context of power. So that would be 20 watts. But if I think about situation number 2, when I do the power, when I complete this amount of work of lifting my box, but I do it in only 1 second, but I still had to do 100 joules of work because it's the same box and I'm lifting at the same distance, that's actually 100 watts. And and so that's how we can bring time into the calculation, and how we can reflect the fact that when I do work, not only is it important to think about how much work I'm doing, but it's also nice to know how can I really bring into play the amount of time that it takes it. And that sometimes is going to be really important. So that's the very simple definition of work. We say that the units that we measure it in are called watts. Now, sometimes you might think about most of the units that we've come we've been exposed to in physics. We're working with metric, and this is still the metric system, but what would be our unit of power that we would be more familiar with? And the answer is horsepower. Now you see that, yeah, that's my car, my engine has this many horsepower, good for you. That's the unit of power. A conversion factor is that 1 horsepower is 746 watts, just in case you're given power in horsepower, but you still need to convert it into some sort of metric measurement. Now, I said that this definition of power was for just average power, but we also have instantaneous power. And I'm just going to make a little bit more room here. We already did this example, so I'm going to get rid of it. And we can express instantaneous power is going to be an increment of work over an increment of time. I know the question has come up in the reading, what does it mean by an increment? Think of calculus and when you learned about integrating, and instead of looking at deltas, which are simply changes over a decent amount of interval, but then we started making those changes smaller and smaller, and then they become an increment, or infinitesimal is another word for it, and it's just talking about a very, very small amount of work that's done for a very small displacement. This is a very small amount of time. You know, you're trying to get it down to 0. But I want to show you something, because the dW, if we imagine the scenario where we're calculating the work done, but remember we had the integral form of work, where work was the integral of the force over the displacement. So it was the integral of force dotted with ds, imagining that the increments of displacement were very small, which by doing that and doing the integration, it allowed us for the possibility that maybe the force is changing, or maybe the orientation between the force and the displacement were changing, and that's why we did that integral. But if we use this to write our increment for the work done, and then we have dt on the bottom, and then you might notice, wait a minute, ds dt looks kind of familiar to me. I can actually write the instantaneous power can be written as the dot product of the force and the velocity. And so sometimes that comes into play where that's going to be something that's useful to us. So that's a little bit about work. What I wanted to do then was to do a little example problem. So this is an example problem out of our book. I think it's example 7.5. I didn't write it down, so I don't want to commit. So we have a car on a hill, and the car has a mass of 1,200 kilograms. And it's traveling up the hill at 90 kilometers per hour. Now, instead of being given the angle of the hill, we're told that it's a 15% grade. And we'll talk about how to work with that. And basically, we want to know how much power do we need to get it up the hill with a displacement of, actually it doesn't really say. We want to take it up the hill at a constant velocity, but this is where we have to also think about 25% of the power is dissipated. What does that mean? It means it's lost. So, you know, this is a situation where we know it's not a perfect world. And so the idea is that there's going to be a certain amount of power that's necessary to get it to go up the hill at a constant velocity, the velocity that we're being given. But then we have to think about the fact that if there's a certain amount of power being delivered to the car, only 75% of that power is going to be able to be used to bring the car up the incline. That 25% that is lost can be lost due to friction, inefficiencies, air resistance, those kinds of things. So there's a certain amount of power that just isn't going to get to be used. And so we have to take that into account. So now we have to start thinking about the forces that are going to be working on this car. So we have, there's the force of gravity, and then there has to be some applied force that makes it go up the incline. If it's going up at a constant velocity, the force that brings it up the incline is going to be equal in magnitude to the x component of the weight. Does that make sense? Because that's actually what it's going to work against. Notice the weight acts straight down. There's going to be a component of the weight related to the angle of the incline. And so we're looking at that x component of weight pulls the car down the incline. If it's going to move at a constant velocity, the force that is going to be responsible for bringing it up the incline is going to be exactly equal to that downward force of the weight. And so now the idea is that we know that the power, and we're going to use this relationship here, is equal to the force times the velocity. So the magnitude of that force is going to be mg sine of theta times the velocity is going to be the power. But I'm not done yet. There's a couple different things I need to do. First of all, we never addressed the issue of the 15% grade. What does that mean? It basically means that a 15% grade means that the tangent of the angle is 0.15. So that's how we figure out what the angle of the incline is. And from that, I basically used to say 0.15, take the inverse tangent of that. And so I found theta is 8.5 degrees. So it's not that big, but when you're going up a hill, you don't want the hills to be too steep. And the other thing we have to do is change the velocity in kilometers per hour into meters per second. And it turns out that this is about 25 meters per second. Hopefully you feel comfortable with doing that, that unit conversion. Now, this would be the power that we need to go up the incline if all of our power was being used to get it up the incline, but we know that we only get 75% of that. And so the way that we account for the 75% of power being used is that, so let's call this the power needed. And I'm going to say the total power I'm going to call P sub t. So basically we'll say 0.75 of the total power that is delivered. So that's going to account for not only the power that's going to be used for getting the car up the incline, but also the power that's dissipated. So if we take 75% of the total power that was delivered by the car, that will be equal to our mg sine of theta times our velocity. And so I can rearrange this to find out what is the total power I need. So does that make sense? So this is the power used is that, and that's equal to how much to get up the incline. But then we can find the total power is going to be equal to the 1,200 kilograms times gravity times the sine of 8.5 degrees times the speed of 25 meters per second, and then we'll divide that by 0.75, And so that's going to allow us to find the total power, which is going to be 58 kilowatts. So keep in mind that would be 58,000 watts. Turns out that the amount of power that we actually get to use, because we don't get to use 58,000 watts, we only get to use a fraction of that to get up the incline, that's actually about 43,000, so, or 43 kilowatts. So my little talk about power and an application, and hopefully you find that useful, and I will see you in class.